You know, every single time you pull up a map on your phone, check the weather, or stream a movie, you are, in a way, having a conversation. A conversation with a satellite that's hundreds, maybe thousands of kilometers up in the sky. But have you ever stopped to think about how that's even possible? I mean, really, how does that connection actually work? Well, let's dive.
So here's the core problem we're up against. A signal leaves a satellite with a decent amount of power. But by the time it travels all the way through the vacuum of space, punches through our atmosphere, what arrives at your phone or your satellite dish is just an unbelievably faint whisper.
And that, right there, is the big question for every single engineer in this field. How on earth do you build a system that can reliably pick up and understand a signal that is almost impossibly quiet? How do you hear that tiny whisper over all the background noise of the universe?
Now this graph, this shows you the beast that engineers are trying to tame. It's called free space path loss. And just look at those curves. As you get farther away or use a higher frequency, the signal strength doesn't just dip a little bit, it absolutely plummets. It's an exponential drop, meaning the signal gets weaker, faster, and faster the farther it goes. It is literally like trying to hear someone whisper during a hurricane. Now, to solve a problem this big, you can't just guess and hope for the best. Engineers use this really powerful, really elegant tool to plan out every single connection. It's called a link budget. And honestly, the best way to think about it is like a balance sheet, but for signal power.
So what is a link budget, really? It's just an accounting problem. On one side of the ledger, you write down everything that boosts your signal, all your gains. And on the other side, you list everything that weakens it, all your losses. And the goal, well, it's pretty simple. You just have to make sure that the gains are bigger than the losses. If they are, you've got a connection.
And this slide just lays it all out, doesn't it? It's this constant balancing act. On the gain side, we can pump more power into the transmitter or use really focused antennas to beam the signal. But the losses side is relentless. You've got that massive distance we talked about, the atmosphere getting in the way, and even things like rain or buildings. The gains have to win this fight, otherwise your signal just vanishes.
And here's what that looks like in the real world. On the left, a high-gain antenna. Think of it like a megaphone for radio waves. It takes the signal and focuses it in one direction. Huge gain. But then you look at the right, and something as simple as a rainstorm can start absorbing that signal, especially at the higher frequencies we use for things like satellite internet. It's a constant tug-of-war.
Okay, so all this theory is great on a whiteboard. But does it actually hold up in the messy, unpredictable real world? Well, to find out, we're going to look at this fantastic project where a group of students put these exact ideas to the test.
So instead of, spending millions of dollars to launch an actual satellite, these students at Nikmetin Erbakan University did something really clever. They used a technology called LoRa, which is just a type of long-range radio, to build a simulator right here on the ground. It was designed to act just like a satellite talking to a ground station so they could test their link budget math in real life. And here's a look under the hood of their system. It's actually beautifully simple. You've got the satellite side with sensors grabbing data like GPS in motion. That info gets fed to a little computer, which then sends it over the LoRa radio link to the receiver, the ground station. It's a perfect little model of a full-blown satellite system. And here are the two main players in our little experiment. On the left, that's the transmitter, their mini satellite, all packed with sensors collecting data. And on the right, you've got the receiver, the ground station. Its only job is to sit there and listen very carefully for that signal and record how strong it is.
All right, so with their gear all built and ready, they took it outside to see what would happen. They planted their ground station in one spot, and then one of them started walking away with the satellite node, all the while measuring the signal strength as the distance grew to nearly 850 meters. And this wasn't an empty field. It was a real environment with buildings, trees, the whole shebang.
And this is where things get really interesting. See, they had their link budget calculations. They had a clean, perfect prediction of what the signal should look like. But now, they had a bunch of real-world measurements. The million-dollar question was, would the two line up?
So, what do you think happened? Did their careful math predict exactly what they'd find? Or did the real world have a few surprises in store for them? And here we go, the moment of truth. That smooth, predictable line, that's what the link budget theory said should happen. And all those scattered dots? Well, that's what actually happened. The theory gave them a pretty good average, a nice baseline. But reality, as you can see, was a whole lot noisier. So,
why the big mess? Why all the scattered points? Well, because out here on the ground, signals don't just travel in a nice, clean, straight line. They bounce off buildings. They get soaked up by trees and walls. They can even get weaker if you're just holding the antenna at a slightly wrong angle. All of these little real-world imperfections add up to create that noisy data we just saw. Now, as our hunger for data from space just keeps growing and growing, this whole challenge of hearing that faint whisper is becoming a serious bottleneck. We need more and more data, faster and faster. So, engineers are looking to something completely different. They're looking to lasers. Look, radio waves have been amazing for us, but the airwaves are getting crowded. There's only so much information you can push through them. So the solution might be to stop using radio waves altogether and switch to, well, light. We're talking about something called free space optics, using focused beams of light, lasers, to send data through space.
And this table really shows you why everyone's so excited about this. With lasers, the data rates are just insane. We're talking gigabits, even terabits per second. That's fast enough to download hundreds of movies in a single second. And because the beam is so tight and narrow, it's incredibly secure, and you don't need to deal with all the complex licensing of radio frequencies. But it does have an Achilles heel. Clouds, fog, bad weather can block the beam.
So think about this. We started this whole journey trying to figure out how we hear a faint whisper from space. But as our demand for data turns that whisper into a roar, the answer might not be to listen harder, but to start watching for a flash of light instead. Is the future of our conversation with the cosmos going to be written not in radio waves, but in lasers?